What if everything we thought we knew about the scale of intelligence in the universe was just small thinking? Picture this: somewhere in the darkness between galaxies, a civilization so advanced, so unimaginably powerful, that they don't just build megastructures around stars, they wrap them around entire galaxies. We've all heard of Dyson spheres, those hypothetical shells built by advanced aliens to harness the energy of their home star. But what if such beings didn't stop there? What if they expanded their reach across billions of stars, weaving a cosmic web so vast it defies human comprehension? This isn't just science fiction, it's a real possibility that could explain some of the deepest mysteries of our universe. Think about the sheer scale of a single galaxy. Our Milky Way alone holds over 100 billion stars, each a potential sun for some distant world. Now imagine a civilization capable of engineering on a level so far beyond us that they could encase not just one star, but every star in their galaxy within an intricate network of energy-harvesting structures. These wouldn't just be Dyson spheres, they'd be Dyson bubbles, expanding across light years, swallowing entire star clusters in their quest for ultimate power. The energy output of such a feat would be staggering, possibly even visible from across the cosmos. And that raises an eerie question: could we already be seeing signs of these galaxy-sized megastructures without even realizing it? The implications are as thrilling as they are terrifying. If such civilizations exist, they'd operate on timescales and technological levels we can barely grasp. They might reshape galaxies like we rearrange furniture, turning entire regions of space into engines of pure computation, vast reservoirs of energy, or even something we can't yet imagine. And here's the most haunting thought of all: what if we're not the first to notice? What if, hidden in the faint glimmers of distant starlight, there are clues pointing to intelligences so vast they've already enclosed their homes in shells of unimaginable scale? That's the journey we're about to take into the realm of alien Dyson bubbles and the breathtaking possibility that entire galaxies might already be under construction by minds greater than our own. But where is everybody? That's the unsettling question at the heart of the Fermi Paradox. If the universe is so vast, with billions of galaxies and trillions of stars, why haven't we found any clear signs of intelligent life? One possible answer is terrifying in its simplicity. Maybe we're looking for aliens the wrong way. We expect radio signals, probes, or spacecraft, but what if advanced civilizations don't operate on those scales at all? Instead, they might leave traces so enormous, so unimaginably large, that we've been staring right at them without recognizing what we're seeing. This is where the concept of megastructures comes in. A Dyson sphere, for example, would be a telltale sign of a civilization harnessing the full energy of its star, something we could potentially detect as an unnatural dimming or heat signature. But if a species could build something like that around a single star, what's stopping them from scaling up? Imagine a civilization millions or even billions of years ahead of us, one that's spread across its entire galaxy. Their energy needs would be colossal, their engineering capabilities beyond anything we can fathom. Instead of just one Dyson sphere, they might construct a vast network of them, a swarm of energy collectors enveloping every star in their reach. Over time, these structures could merge, forming a shell not just around individual stars, but around entire galactic regions, a Dyson bubble on a scale so massive it blurs the line between natural and artificial. And here's the twist: we might already be seeing hints of this. Astronomers have spotted galaxies with bizarre infrared signatures, emitting far more heat than expected. Some have unusual gaps in their light curves, as if something is blocking or redirecting starlight in ways that don't match natural explanations. Could these be the fingerprints of galaxy-spanning megastructures? Or are we just finding more cosmic mysteries with simpler answers? The truth is, we don't know yet, but the fact that we're even asking the question changes everything. It forces us to rethink what intelligence looks like at the grandest scales and whether we've been missing the signs because we weren't looking big enough. The Fermi Paradox isn't just about the silence of the cosmos, it's about the limits of our imagination. If civilizations can grow to dominate galaxies, then their absence might not be an absence at all, just a failure to recognize their presence. Maybe they're not hiding, maybe they've been here the whole time, written across the sky in structures so vast we mistook them for the universe itself. Freeman Dyson first proposed his revolutionary idea back in 1960, and it was so radical at the time that it blurred the line between science fiction and real astrophysics. He suggested something astonishing. What if a civilization advanced enough didn't just live on planets or build stations near stars, but instead constructed a massive shell or swarm of structures around their entire sun? The purpose: to capture every bit of energy radiating from it. Think about the sheer scale of that ambition. Our sun alone emits enough energy in a single second to power human civilization for thousands of years, and a Dyson sphere would tap into all of it. At its core, the concept is simple. If a civilization grows powerful enough, its energy demands would eventually outstrip what planets could provide, so why not go straight to the source? A Dyson sphere wouldn't necessarily be a solid shell, despite how it's often depicted in movies. It could be a vast swarm of solar collectors, orbiting mirrors, or even an intricate lattice of energy-harvesting satellites, all working together to siphon a star's output. The key idea is expansion, not just building one structure but many, until the entire star is enveloped in a kind of engineered cocoon. Modern astrophysics has taken Dyson's original vision even further. Scientists now speculate about Dyson swarms, dense clouds of energy capturing megastructures, or even partial rings that could be easier to detect from interstellar distances. Some researchers suggest these constructs might emit unusual infrared radiation, since all that captured energy has to go somewhere, likely being re-radiated as waste heat. That's why when astronomers scan the cosmos for signs of advanced civilizations, they don't just look for radio signals, they search for stars that glow a bit too dim in visible light but suspiciously bright in infrared. But here's where it gets even more fascinating. A Dyson sphere isn't just about energy, it's about real estate. A single structure like this could provide living space on an unimaginable scale, trillions upon trillions of times the surface area of Earth. Entire civilizations could thrive on its inner surface, bathed in perpetual sunlight. And if that's possible around one star, what stops a species from repeating the process across their whole galaxy? That's the terrifyingly grand vision we're starting to grapple with, not just spheres around stars, but bubbles around galaxies. Dyson's original idea may have been bold, but it was only the beginning. The true scale of what might be out there could dwarf even our wildest imaginations. So if harnessing the energy of a single star seems like an impossible engineering feat, try wrapping your mind around this. What would it take to scale up from a Dyson sphere to something a billion times larger? The jump from stellar to galactic megastructures isn't just about size. It's about rewriting the fundamental rules of what we consider possible for an advanced civilization. First, consider the raw numbers. A typical galaxy contains hundreds of billions of stars spread across hundreds of thousands of light years. Building individual Dyson spheres around even a fraction of those stars would require more material than exists in multiple solar systems. But here's where things get interesting. A sufficiently advanced civilization might not need to construct each one manually. Imagine self-replicating machines, tiny at first, but programmed to harvest local resources and build copies of themselves. Given enough time, and we're talking millions, perhaps billions of years here, these machines could spread exponentially, converting entire star systems into energy-harvesting nodes without direct oversight. Energy isn't the only hurdle, though. Time and coordination on galactic scales introduce staggering complications. Light itself takes tens of thousands of years just to cross from one side of a galaxy to another, meaning any centralized control would be impossible due to the delay in communication. The solution, a decentralized, almost hive-like intelligence, where each Dyson sphere acts autonomously yet contributes to a larger network. Picture trillions of independent megastructures, each humming along according to local conditions but still part of a vast, galaxy-spanning energy grid. And then there's the question of waste heat. Even a single Dyson sphere would irradiate enormous amounts of thermal energy. Now multiply that by billions. The sheer infrared glow of such a civilization could outshine the natural light of their galaxy, potentially making them visible across the observable universe. Some astronomers theorize that this might explain certain anomalous galaxies we've already spotted, ones that emit far more infrared radiation than expected while appearing dim in visible light. But perhaps the most mind-bending implication of all is that a Dyson bubble wouldn't just be a power source, it could fundamentally reshape the galaxy itself. Stars might be moved into optimal configurations, dust and gas harvested for construction, even black holes repurposed as cosmic engines. The line between natural structure and artificial design would blur until the entire galaxy became, in essence, one vast machine. And if that sounds like the plot of a far-future sci-fi epic, well, that's exactly why this idea forces us to expand our thinking beyond human scales and into the realm of civilizations operating on cosmic timeframes. The terrifying beauty of this concept is that it challenges everything we assume about the limits of intelligence. Maybe the universe isn't silent at all. Maybe we've just been listening for whispers when the real message has been written in galaxies all along. To understand just how mind-bending the idea of galaxy-sized megastructures really is, we need to step back and look at one of the most ambitious frameworks for classifying intelligent life, the Kardashev Scale. Proposed by Soviet astronomer Nikolai Kardashev in 1964, this simple but powerful system ranks civilizations based on how much energy they can harness. A Type 1 civilization uses all the energy available on its home planet. A Type 2 masters its entire star system. Think Dyson spheres, but it's the Type 3 civilization that truly bends reality, a species capable of controlling energy on the scale of its entire galaxy. Now here's where it gets wild. If a species reached Type 3 status, they wouldn't just build megastructures, they'd transform their galaxy into one. Picture an entire Milky Way not as a collection of random stars, but as a carefully engineered network, with every sun wrapped in energy-harvesting structures linked together in a vast humming grid. The Dyson bubble hypothesis takes this even further. What if these civilizations don't just build individual spheres, but merge them into a seamless, galaxy-encompassing system? Instead of stars shining freely into space, their light would be captured, processed, and repurposed on scales we can barely compute. But how would we even recognize such a civilization? That's the haunting question. A galaxy fully harnessed by a Type 3 species wouldn't look like the spirals we're used to seeing in telescopes. It might glow unusually in infrared as waste heat radiates from countless energy collectors. Or perhaps vast regions would appear unnaturally dark, with starlight blocked by megastructures we can't yet comprehend. Some astronomers argue we might have already spotted candidates galaxies like Messier 82, which emits bizarrely high levels of infrared radiation, or others with unexplained gaps in their visible light. Could these be cosmic construction zones where entire sections of the galaxy have been repurposed? The terrifying beauty of the Kardashev Scale is that it forces us to confront the limits of our own imagination. We're a species just barely scratching at Type 1 status, still burning fossil fuels while dreaming of solar satellites. But out there, in the deep dark, there might be minds operating on timelines of millions of years, treating stars like building blocks and galaxies as raw material. The absence of obvious alien signals might not mean we're alone. it might just mean we're not yet capable of recognizing the signatures of something so vastly beyond us. After all, would an ant understand a skyscraper? And that's the spine-tingling possibility lurking behind the Dyson bubble hypothesis. We're not just searching for aliens, we're searching for architects of reality itself, beings who might have already turned their home galaxies into something we wouldn't even recognize as artificial. The universe might not be empty, it might just be filled with wonders too big for us to see. The universe is full of mysteries, and some of them might be hiding in plain sight. Take Galaxy NGC 4860, for example. It emits an unusual amount of infrared radiation, far more than its visible light output suggests. Normally, galaxies glow predictably across the electromagnetic spectrum, but this one is different. It's as if something is absorbing its starlight and re-emitting it as heat. Could this be the thermal fingerprint of a civilization harnessing the energy of countless stars? Or is there a simpler explanation, like massive dust clouds or intense star formation? The truth is, we don't know yet, but the fact that these anomalies exist at all makes the question worth asking. Then there's the case of Galaxy KIC 8462852, nicknamed the Dyson Sphere candidate after astronomers noticed its light dimming in bizarre, irregular patterns. Instead of the smooth curves expected from orbiting planets or natural debris, this star's light drops dramatically, sometimes by up to 20%, in ways that don't match any known astrophysical phenomenon. Some researchers have suggested these dips could be caused by vast swarms of energy collectors passing in front of the star and blocking its light in fragments. Skeptics argue it might just be an unusually dense cluster of comets, but the sheer scale of what would be required strains credulity. Either way, the mystery remains unsolved. Even more intriguing are the galaxies that seem to be missing starlight altogether. Surveys of the cosmos have turned up regions where the expected glow of billions of stars is strangely absent, like cosmic voids where something is intercepting the light before it reaches us. One theory: these could be zones where Dyson bubbles have reached near total coverage, their megastructures so thickly clustered that they block starlight entirely, rerouting it into energy grids we can't yet detect. Of course, alternative explanations exist: intervening dust, black holes, or even errors in our observations, but the possibility lingers like a shadow at the edge of our understanding. What makes these anomalies so tantalizing is that they don't just defy expectations, they do so in ways that align eerily well with theoretical predictions about galaxy-scale megastructures. Infrared excess, unnatural dimming, missing starlight, each fits a potential signature of a civilization engineering its home galaxy into something unrecognizable. And while Occam's razor suggests we should favor natural explanations first, the sheer scale of these phenomena forces us to wonder, at what point does coincidence become evidence? The search for Dyson bubbles isn't just about spotting weird data, it's about redefining what counts as a sign of intelligence. If a species could reshape its galaxy, its artifacts wouldn't look like flying saucers or radio signals. They'd look like physics itself breaking the rules, whispering to us in the language of missing light and unexplained heat. And that's the real challenge, not just finding these cosmic fingerprints, but daring to consider that they might be more than dust and chaos. They might be the handwriting of giants. Dark matter is one of the greatest enigmas in modern astrophysics, an invisible substance that makes up roughly 85% of the universe's mass, yet refuses to reveal itself except through its gravitational pull. Scientists have spent decades searching for it, proposing everything from exotic particles to hidden dimensions. But what if we've been thinking about this all wrong? What if some of the phenomena we attribute to dark matter aren't the work of mysterious physics, but of unfathomably advanced civilizations engineering their galaxies on scales we can barely comprehend? Take gravitational lensing, for example. When light from distant galaxies bends around massive objects in space, it creates distorted, magnified images like cosmic mirages. Traditionally, we assume this bending is caused by the gravity of dark matter halos surrounding galaxies. But here's the twist: that same warping could theoretically occur if a galaxy were encased in a dense swarm of megastructures, each one massive enough to curve spacetime. The math isn't identical. Engineered objects would have different density distributions than dark matter, but at interstellar distances, the effects might look eerily similar through our telescopes. Or consider the missing satellite problem. Our models predict that galaxies like the Milky Way should be surrounded by hundreds of small, dark matter-dominated dwarf galaxies. Yet we've only found a fraction of them. Could the missing satellites simply be obscured by vast Dyson swarms, their starlight absorbed and repurposed by galaxy-spanning civilizations? It's a radical idea, but not impossible. After all, if a species had the technology to enshroud entire star clusters, hiding a few dwarf galaxies would be trivial by comparison. This isn't to say dark matter doesn't exist. The evidence for it is overwhelming, from galaxy rotation curves to the cosmic microwave background. But science thrives on questioning assumptions, and the possibility that some dark matter signatures might overlap with megastructure signatures is too tantalizing to ignore. Maybe we're not just mapping the invisible scaffolding of the universe. Maybe we're glimpsing the shadows of something far stranger. The real challenge lies in distinguishing one from the other. Natural dark matter bends light smoothly, while artificial megastructures might produce more irregular distortions. Natural dark matter gathers in predictable halos, while Dyson swarms could cluster in patterns reflecting intentional design. Future telescopes like the Vera Rubin Observatory or the James Webb successors might spot these subtle differences if we know what to look for. This is where the debate gets thrilling. Scientists arguing for conventional dark matter point to its explanatory power across countless observations. Those open to the megastructure hypothesis counter that extraordinary claims require extraordinary evidence, but also that extraordinary technology might leave extraordinary traces. Both sides agree on one thing: the universe is far weirder than we've imagined. Whether the truth lies in undiscovered physics or undiscovered civilizations, the answer will rewrite our place in the cosmos. So next time you hear about dark matter's ghostly grip on galaxies, pause for a moment. Ask yourself, are we studying the universe as it naturally is, or as something or someone has shaped it to be? The line between nature and engineering might be thinner than we think. Enclosing an entire galaxy isn't just an engineering challenge, it's a direct confrontation with the fundamental laws of physics. Start with the sheer amount of material needed. The Milky Way contains roughly 200 billion stars, each separated by light years of empty space. To build even a basic Dyson swarm, around 1% of them, you'd need to dismantle entire planets for raw materials, millions of them. The numbers become absurd quickly. Constructing a partial shell around a single star might require the mass of Jupiter. Scale that up to galactic proportions, and you're talking about harvesting the equivalent of several dwarf galaxies worth of matter. Where would a civilization even find that much usable material without tearing apart their own cosmic neighborhood? Then there's the problem of energy distribution. Even if you could build megastructures across a galaxy, coordinating their power flow is another nightmare. Light itself takes 100,000 years to cross from one side of the Milky Way to the other, meaning real-time control is impossible. Any civilization attempting this would need a decentralized network so advanced, it makes our internet look like stone tools. Imagine self-adjusting solar collectors, each autonomously storing and redirecting energy across interstellar distances, forming a kind of galactic power grid where no single point can fail the system. The computing power alone would dwarf anything we've conceived, but the real kicker, thermodynamics, doesn't care how advanced you are. All that captured starlight has to go somewhere, and waste heat is inevitable. A single Dyson sphere might irradiate energy as infrared, but a galaxy's worth would glow like a beacon across the universe. The heat signature would be so extreme, it might actually limit how much energy you could practically use. Too much concentration, and you'd vaporize your own infrastructure. Some theorists suggest such civilizations might need to vent heat into intergalactic space or even harness black holes as cosmic radiators, dumping excess energy beyond the event horizon where it effectively disappears from the universe. And let's not forget gravity's role. Megastructures orbiting stars are one thing, but at galactic scales, the gravitational dance becomes chaotic. Stars don't sit still. They whirl around the galactic center at hundreds of kilometers per second, their orbits shifting over eons. Any fixed network of energy collectors would be torn apart by these forces unless actively stabilized. The solution may be dynamic megastructures that adjust their orbits like a flock of birds, or even repositioning stars themselves to maintain optimal configurations. It sounds like science fiction, but for a Type 3 civilization, moving stars might be no harder than we rearrange furniture, the most humbling realization. Our laws of physics might be irrelevant to them. We assume they're bound by the same constraints: conservation of energy, the speed of light, entropy's relentless march. But what if they've discovered loopholes we haven't dreamed of, manipulating dark energy, tapping into zero-point energy, or even rewriting the rules at a quantum level? A galaxy enclosed by such beings wouldn't just defy our expectations, it might operate on physics we'd struggle to recognize as real. That's the haunting beauty of this thought experiment. It forces us to confront not just the limits of technology, but the limits of our imagination. The universe doesn't owe us intelligibility. If civilizations exist that treat galaxies as raw material, their engineering might look less like construction and more like alchemy, transforming reality itself into something new. Harnessing the energy of billions of stars isn't just about scaling up, it's about redefining what energy even means. Picture this: a civilization that doesn't just consume power but orchestrates it, weaving starlight into a seamless galaxy-wide symphony. Each star in their dominion becomes a single note, its output fine-tuned and directed not just for heat or electricity, but for purposes we might struggle to comprehend. The first challenge is collection. A single Dyson swarm around a star might consist of trillions of orbiting solar panels, but multiply that by billions of stars and the logistics become staggering. One solution: self-replicating nanomachines, tiny architects programmed to harvest asteroids, comets, even gas giants, converting raw material into energy collectors faster than natural processes could ever match. Over millennia, these machines could fan out across star systems, building autonomously until every sun is encircled by a humming lattice of light-capturing technology. But gathering energy is only half the battle. Storing and transferring it across light years requires breakthroughs beyond our current physics. Imagine quantum energy networks where power is teleported instantly between nodes using entangled particles, or space-time itself manipulated to create shortcuts for energy flow. A civilization at this level might treat the fabric of the universe like a circuit board, bending it to shunt power where it's needed without the delays imposed by light speed. Then comes utilization. For us, energy powers cities and devices. For them, it might fuel megascale computation, simulating entire universes inside black hole-powered quantum matrices. Or perhaps they've moved beyond physical forms entirely, existing as pure information patterns riding the currents of captured starlight, their consciousness distributed across the very structures harvesting the galaxy's energy. Their technology wouldn't resemble machines as we know them. It would look like physics itself behaving strangely, stars dimming on command or nebulae flickering in deliberate patterns. The most unsettling implication: waste becomes impossible at this scale. Every joule of energy, every photon of heat would be recycled with near-perfect efficiency. Their Dyson bubble wouldn't just be a power grid, It'd be a closed ecosystem where even the infrared glow of waste heat is captured and repurposed, the only signature they couldn't hide. The absence of natural starlight, the eerie voids where galaxies should shine but instead whisper the presence of something far greater. This isn't just energy harvesting. It's the universe being rewritten one star at a time into something we might not even recognize as technology. And that's the most thrilling possibility of all, that advanced civilizations don't announce themselves with radio signals, but by quietly turning the cosmos into something new. Mathematical models of Dyson bubbles push the limits of what we consider possible in cosmic engineering. Picture a galaxy not as a scattering of stars, but as a meticulously designed energy network, each sun a node in a vast computational or power grid. Theorists have attempted to simulate such structures, and the results are as fascinating as they are mind-bending. One approach suggests a fractal-like design, where smaller Dyson swarms around individual stars link into ever larger clusters, forming a hierarchical web that scales up to galactic proportions. This wouldn't just be a haphazard collection of megastructures, but an interconnected system, almost like a neural network writ large across the cosmos. Another model explores the idea of a dynamic shell, a shifting, adaptive envelope that responds to the movement of stars within the galaxy. Since stars orbit the galactic center at different speeds, a rigid structure would tear itself apart over time. Instead, simulations show that a flexible swarm of megastructures, constantly adjusting their positions to maintain optimal energy capture, could theoretically endure for billions of years. Think of it like a school of fish where each individual moves in harmony with the group, creating a cohesive whole despite constant motion. Then there's the question of shape. Would a Dyson bubble be spherical, enveloping the galaxy in a uniform shell, or might it take on a more complex geometry like a torus or a series of linked rings? Some simulations suggest that a spiral arm configuration could mimic the galaxy's natural structure, concentrating megastructures along the densest stellar pathways while leaving quieter regions open. This would allow for efficient energy collection where stars are most abundant, reducing the material needed to cover less populous areas. Energy flow within these models is another staggering challenge. A galaxy-sized Dyson bubble wouldn't just capture light, it would need to redistribute it across incomprehensible distances. One hypothetical solution involves quantum energy tunneling, where power is transmitted instantaneously between points using entangled particles. Another wild idea, harnessing spacetime itself, creating wormhole-like conduits to bypass light-speed delays. These concepts sound like pure sci-fi, but for a civilization capable of enclosing galaxies, they might be as routine as power lines are to us. Of course, all these models come with caveats. The sheer scale introduces chaos stellar collisions, supernova, black holes, any of which could disrupt megastructures on catastrophic scales. Simulations that account for these variables show that maintenance would be a never-ending task, requiring autonomous repair systems capable of rebuilding shattered energy collectors in real time. It's a reminder that even the most advanced civilizations would still wrestle with entropy's relentless grind. What's most striking about these simulations isn't just their complexity, but what they reveal about our own limitations. We're trying to imagine technologies that operate on timescales longer than human history, engineered by intelligences that might think in millennia the way we think in minutes. The math might check out, but the mindset required to envision such projects, that's the real frontier. Every equation we write is a whisper from a species still tethered to its home planet, trying to decode the blueprints of gods. Of course, not every strange glow or missing star points to alien megastructures. The universe is full of natural phenomena so bizarre they could easily masquerade as signs of cosmic engineering. Take starburst galaxies, for example, regions where stars are being born at a frenzied rate, filling space with thick clouds of dust that absorb visible light and re-emit it as infrared radiation. From a distance, the signature looks eerily similar to what we'd expect from a galaxy encased in Dyson swarms. The key difference, starburst activity, tends to be concentrated in specific zones like galactic cores, while an artificial enclosure would likely spread more uniformly. Still, without high-resolution observations, the two could be easily confused. Then there's the role of supermassive black holes. When these monsters feed, they don't just swallow matter. They squeeze it into blazing disks of plasma hotter than a million suns, surrounded by donut-shaped rings of dust. The energy pouring out can outshine an entire galaxy, and the surrounding dust irradiates that energy as infrared light. Some quasars and active galactic nuclei match the very same thermal profiles that theorists predict for Dyson bubbles. Even stranger, black holes can warp spacetime so severely that they act like cosmic lenses, bending and magnifying light from objects behind them in ways that mimic the gravitational distortions of megastructure swarms. Dark nebulae, massive clouds of cold gas and dust add another layer of ambiguity. These cosmic murk zones block starlight entirely, creating patches of eerie darkness that could be mistaken for sections of a Dyson bubble under construction. The Coalsack Nebula, for instance, looks like a hole punched through the Milky Way starfield. And when such clouds drift in front of distant galaxies, they can produce the same missing starlight effect that might otherwise hint at megastructures. The difference lies in the details. Natural dust scatters certain wavelengths predictably, while artificial constructs might block light more selectively. Even more exotic possibilities lurk in theoretical physics. Cosmic strings, hypothetical, spaghetti-thin defects in spacetime left over from the Big Bang, could produce gravitational lensing effects resembling those of massive artificial structures. Or consider primordial black holes, tiny yet dense relics of the early universe, which might cluster in ways that mimic the shadows of Dyson swarms. And let's not forget the wild card, vacuum decay. If some distant galaxy triggered a bubble of true vacuum expansion, the phase transition's energy release could, in principle, look like an unnatural infrared glow. The lesson here is humility. Nature is a master of illusion, capable of conjuring phenomena that defy our expectations without any intelligence behind them. That doesn't mean galaxy-scale megastructures aren't out there, only that the universe demands we rule out the mundane before leaping to the extraordinary. The search for alien Dyson bubbles isn't just about spotting anomalies. It's about peeling back layer after layer of cosmic mystery until only the truly inexplicable remains. And that's where things get really interesting. In the spiral arms of the constellation Cetus, a galaxy named NGC 247 spins quietly, but something about it doesn't add up. At first glance, it looks like any other dwarf galaxy, its stars twirling in predictable patterns, but peer closer and the anomalies start piling up. For decades, astronomers have noticed that parts of NGC 247 emit far more infrared radiation than visible light, as if something is absorbing its starlight and re-radiating it as heat. That's exactly the kind of fingerprint theorists predict for a galaxy partially enclosed by Dyson swarms, yet the truth might be even stranger. The smoking gun lies in NGC 247's core. Most galaxies shine brightest at their centers, where stars cluster densely around supermassive black holes. But here, the core is oddly dim, almost as if something is blocking the light. Surrounding this dark region, a halo of intense infrared glow, like a cosmic heat shield radiating the energy it's captured. Some researchers argue this could be the signature of megastructures in progress, vast arrays of solar collectors built around the galaxy's central stars, their waste heat lighting up our telescopes in ways nature struggles to explain. But skeptics have counter-arguments. NGC 247 is also a hotspot for star formation, and newborn stars are often shrouded in thick dust clouds that absorb and re-emit light similarly. The galaxy's unusual profile might just be the chaos of stellar nurseries, not alien engineering. Then there's the void near its center, a region where stars seem suspiciously sparse. Could this be a construction zone cleared of stars to make room for megastructures? Or is it simply a chance gap, the kind that forms naturally when orbital dynamics leave pockets of emptiness? The debate intensifies when you examine the galaxy's motion. Stars on one side of NGC 247 move differently than those on the other, as if tugged by invisible masses. Dark matter is the usual suspect, but what if some of that gravitational distortion comes from artificial structures, Dyson swarms so dense they bend spacetime like invisible planets? It's a tantalizing thought, though proving it would require detecting patterns in the starlight that natural phenomena can't replicate. Perhaps the most compelling clue is timing. NGC 247 isn't just weird, it's weird in ways that align eerily with models of how a Type 3 civilization might expand. Simulations suggest such a species would likely start by harnessing their galaxy's core, where stars are most concentrated before fanning outward. That's exactly what we seem to see here, a dim center with escalating infrared emissions at the edges, like a wave of construction radiating from the heart of the galaxy. Of course, extraordinary claims demand extraordinary evidence, and right now, NGC 247 remains a puzzle with multiple possible solutions. It could be a galaxy midway through an unnatural transformation, or it might just be a cosmic Rorschach test reflecting back our own hopes for what's out there. But that's the thrill of the hunt. Every anomaly like this forces us to sharpen our tools, refine our questions, and confront the humbling idea that the universe might be hiding wonders beyond our wildest guesses. The next time you look up at the night sky, remember, somewhere out there, NGC 247 spins silently, keeping its secrets for now. But with every new telescope, every upgraded algorithm, we get closer to answering the most thrilling question of all: are we alone, or is someone out there reshaping the stars? If we're searching for civilizations that have wrapped their galaxies in cosmic megastructures, we need to rethink what signs of intelligence actually look like. Traditional SETI efforts focus on narrowband radio signals or laser pulses, the kind of deliberate hello a young civilization like ours might send. But a species capable of building Dyson bubbles operates on such a vastly different scale that their signatures could be written in the very fabric of their galaxy. Take infrared radiation, the thermal glow of waste heat. A galaxy encased in energy-harvesting megastructures would theoretically emit far more infrared than visible light, since most starlight would be captured and converted. This isn't just speculation. Astronomers already have instruments like NAS, a wide-field infrared survey explorer scanning the skies for exactly these anomalies. The trick is distinguishing between natural heat sources like dust clouds or starburst regions and unnatural ones. One telltale sign: artificial structures would likely radiate heat at specific, uniform wavelengths, while cosmic dust emits a broader, messier spectrum. But infrared isn't the only clue. Gravitational microlensing surveys might reveal another fingerprint. If millions of Dyson swarms orbit a galaxy's stars, their combined mass could subtly bend the light from background objects in ways that differ from dark matter's smooth distribution. The European Space Agency's Gaia mission, mapping billions of stars with unprecedented precision, could potentially spot these minute distortions, like catching shadows of invisible giants moving through a cosmic fog. Then there's the starlight itself. A partially enclosed galaxy might show unnaturally sharp dips in brightness when observed over time, as megastructures pass in front of their stars. The Kepler Space Telescope's observations of Tabby's star, with its bizarre, irregular dimming, gave us a taste of how this might look. Scale that up to an entire galaxy, and the light curves could reveal vast geometric patterns, like the shadow of a machine larger than anything nature builds alone. Even more speculative are signs of directed energy. Some theorists suggest advanced civilizations might use captured starlight not just for power, but for propulsion-firing beams to push interstellar ships or even reposition stars. These beams, if misaligned with their targets, could flash across the universe like cosmic lighthouses. Breakthrough Listen surveys now scan for such transient pulses, not just steady radio signals. The challenge, of course, is separating the impossible from the merely improbable. When a galaxy like Messier 82 emits 50 times more infrared than expected, is it a sign of alien industry or just an unusually active stellar nursery? The key lies in cross-referencing multiple anomalies, infrared excess paired with unnatural light curves, microlensing events that can't be explained by dark matter alone. It's detective work on a galactic scale, where each clue might be a whisper of intelligence rewriting the rules of astrophysics. Perhaps the most profound shift is in how we define signal. We're not listening for messages anymore, we're reading the energy budget of entire galaxies, searching for thermodynamic footprints that shouldn't exist. In a universe where the most advanced civilizations might not bother speaking, their megastructures could be shouting in a language we're only just learning to hear. Reshaping an entire galaxy isn't just an engineering challenge, it's a moral earthquake. Picture a civilization so advanced it treats stars as raw materials and entire star clusters as construction zones. The power to rewire something as vast as a galaxy comes with dilemmas we're only beginning to grasp. What happens to the countless worlds orbiting those stars? Are they dismantled for resources or preserved like artifacts in a cosmic museum? The ethical weight of such choices is staggering. For a species capable of galactic engineering, the line between godlike creation and catastrophic overreach might be thinner than a neutron star's crust. Consider the rights of other life forms. Even if a civilization avoids outright destruction, altering a galaxy's structure could unintentionally destabilize habitable zones, triggering supernova or redirecting deadly radiation toward unsuspecting worlds. Imagine a distant planet teeming with primordial life, only to have its sun repositioned for someone else's energy grid, its evolutionary trajectory shattered by decisions made light years away. Does might make right in the cosmos, or would a truly advanced species recognize some form of interstellar stewardship, a moral code that extends beyond their own survival? Then there's the risk of runaway consequences. Galaxies are dynamic systems where tugging on one star can ripple across millennia. A civilization might build a Dyson swarm to harness energy, only to inadvertently disrupt the orbits of neighboring systems, flinging planets into darkness or colliding stars like billiard balls. The scale of potential collateral damage is incomprehensible. Think of it as cosmic deforestation, but with entire solar systems as the trees. Could a species with such power resist the temptation to optimize everything, or would they inevitably turn their home galaxy into a machine, silencing the natural chaos that births new stars and planets? And what of the universe itself? If multiple civilizations reach this level of mastery, their projects could collide in ways no one foresaw. Competing Dyson bubbles might overlap, triggering energy wars fought with redirected quasars or black hole slingshots. The Milky Way could become a chessboard for entities we can't even perceive, their conflicts written in the ruins of rearranged constellations. It's a sobering thought. The same technologies that could unite a galaxy might also fracture it. Yet there's another side to this, a vision of galactic engineering as the ultimate act of nurture. A civilization that masters such power might use it to extend life's reach, seeding barren worlds with engineered ecosystems or shielding fragile planets from cosmic threats. They could become gardeners on a scale that dwarfs our wildest myths, tending not just to their own kind but to the flourishing of life itself. The choice between conquest and caretaking would define their legacy across eons. Here's the haunting question at the core of it all. Does intelligence at its highest level inevitably reshape its environment into submission, or does it learn to harmonize with the universe's natural rhythms? We might never know, but the fact that we're asking reveals something profound about our own place in the cosmos. Even as a fledgling species, we're already grappling with the ethics of power we don't yet possess. That self-awareness, more than any megastructure, could be the true marker of intelligence worth reaching for the stars. Building a structure around a single star is a project spanning centuries but encasing an entire galaxy. That requires timescales so vast they stretch the limits of a civilization's endurance. Think about humanity's own trajectory. Just 5,000 years ago, we were building pyramids with stone tools. Today, we're sending probes beyond our solar system. Yet, even at this pace, the jump from planetary to galactic engineering would demand not just technological leaps, but something far more fragile: continuity. A species attempting to wrap its galaxy in megastructures isn't just fighting physics, it's racing against its own mortality. The numbers are staggering. Even with self-replicating machines working at near light speeds, constructing a Dyson swarm around one star might take millennia. Now multiply that by billions. The sheer coordination required to sustain such an effort across hundreds of thousands of light years introduces another hurdle: time dilation. Instructions sent from one side of the galaxy would take eons to reach the other. A civilization would need to decentralize completely, trusting autonomous systems to operate independently for generations without guidance or oversight. One misstep, a war, a plague, an AI rebellion could derail the entire project, leaving half-built megastructures to crumble into cosmic debris. And then there's evolution itself. Would a species even remain recognizable over such spans? The humans who laid the first stones of Stonehenge wouldn't recognize our world today. Now imagine a billion years of cultural and biological change. The minds that begin a galactic enclosure might be as alien to their descendants as bacteria are to us. Would future generations still care about the project, or would their priorities shift beyond recognition? A Dyson bubble isn't just a test of engineering, it's a gamble that a civilization's core drive will outlast the rise and fall of countless eras. Yet some argue longevity might not be the bottleneck we assume. Advanced civilizations could transcend organic limits, merging with machines or digitizing consciousness to escape biological decay. Imagine minds backed up across redundant servers, surviving supernova by migrating between stars, their ambitions unfazed by time. Or perhaps they'd engineer synthetic successors, AI custodians programmed to complete the project no matter how long it takes. In this scenario, the builders might not be alive to see completion, but their legacy would endure in the cold, patient logic of machines. There's another possibility: collaboration. If multiple civilizations arise within a galaxy, they might pool resources and knowledge, sharing the burden across generations. Picture a galactic cooperative where species rise and fall, but the work continues, passed like a torch between cultures separated by epochs. The traces of such partnerships might be hidden in the very structures themselves, layers of technology reflecting different eras, like an archaeological dig written in solar panels and orbital mirrors. The most haunting question isn't whether a civilization can survive long enough to build a Dyson bubble, but whether any would choose to. Faced with a void of deep time, would they pour their energies into reshaping the galaxy or seek escape beyond it? Some theorists suggest the Great Silence isn't evidence of absence. It's the sound of civilizations vanishing into simulations, pocket universes, or dimensions we can't perceive. A galaxy wrapped in megastructures might not be the pinnacle of achievement, but a relic abandoned by those who moved on to stranger frontiers. As we peer into the night sky, we're not just searching for other builders. We're confronting the limits of our own endurance and wondering whether any dream can outlast the stars themselves. What if Dyson bubbles aren't the end point of cosmic engineering, but merely the beginning? The same logic that leads us to imagine civilizations enclosing single galaxies could scale up infinitely to clusters, superclusters, and beyond. Picture a web of megastructures so vast they stitch together entire galactic neighborhoods, turning colliding spirals and elliptical giants into pieces of some incomprehensible machine. Consider the Coma Cluster, a gathering of over 1,000 galaxies bound by gravity, each one potentially wrapped in its own Dyson swarm. Now imagine those swarms linking across intergalactic space, forming a superstructure that treats the void between galaxies not as empty distance, but as wiring in a circuit bigger than our observable universe. The energy requirements for such a project would dwarf anything we've discussed so far, but so would the rewards. A civilization capable of this wouldn't just harness starlight. They might tap into the kinetic energy of galaxies in motion, the radiation pouring from active galactic nuclei, even the dark energy accelerating cosmic expansion itself. The real shock comes when you realize we might already be seeing hints of this. Some galaxy clusters emit bizarrely uniform radio signals spanning millions of light years. Synchrotron radiation that theoretically could come from particle accelerators the size of galactic filaments. Others show strange alignments in their polarization, as if something is imprinting large-scale structure on the universe's very fabric. Most provocatively, certain superclusters appear to have regions where the Hubble flow, the normal expansion of space, seems locally altered, almost as if something is counteracting dark energy's pull on specific scales. Of course, natural explanations exist for all these phenomena, but the unsettling possibility remains. What if we're not looking at cosmic accidents, but engineering projects so vast they manipulate the scaffolding of reality itself? The same way an ant can't comprehend a city, we might be surrounded by evidence of intelligence operating on scales that render individual galaxies insignificant. This raises profound questions about limits. Could even a Type 3 civilization master of its own galaxy achieve such feats? Some physicists speculate that truly intergalactic engineering would require technologies beyond our current understanding of physics. Manipulation of cosmic strings for faster-than-light connections, harvesting energy from quantum foam fluctuations, or even rewriting the fundamental constants in localized regions of space. The energy demands alone might necessitate tapping into alternate universes or higher dimensions. Yet if such civilizations exist, their very presence could explain one of cosmology's greatest mysteries, why the universe appears so finely tuned for life. Perhaps the laws we observe aren't fundamental at all, but the carefully maintained parameters of an older intelligence's ongoing project. In this scenario, galaxies wouldn't just be enclosed. They'd be nodes in a network spanning all of creation, with our observable universe just one subroutine in a cosmic program running on hardware we can't begin to fathom. The most humbling thought, if structures like this exist, they might not just transcend space, they could defy time. A civilization that learned to engineer on intergalactic scales might have found ways to escape heat death, recycling entropy itself into new usable energy across aeons. Their megastructures could outlast stars, surviving in some form even as the universe grows cold and dark. So when we peer through telescopes at the large-scale structure of the cosmos, those glittering filaments and voids stretching billions of light years, we might be seeing more than nature's handiwork. We could be staring at the unfinished edges of a project whose full scope makes galaxies look like atoms. And that realization changes everything, not just about where we look for life, but what we consider life to be. The idea of Dyson spheres and bubbles has long fascinated not just scientists, but storytellers fueling some of the most ambitious visions in science fiction. One of the earliest and most iconic depictions comes from Larry Niven's Ringworld, where a massive artificial ring encircles a star, providing living space on a scale that dwarfs planets. While not a full Dyson sphere, Niven's creation captured the imagination with its sheer audacity, planting the seed in popular culture that megastructures could redefine how civilizations inhabit space. Star Trek took the concept even further. In the Next Generation episode Relics, the crew encounters a dormant Dyson sphere, its interior surface lit by a captive sun, a visualization that brought Freeman Dyson's theoretical idea to life for millions of viewers. The eerie, abandoned grandeur of the structure hinted at a lost civilization's rise and fall, turning the Dyson sphere into a symbol of both technological triumph and cosmic melancholy. But perhaps the most striking fictional treatment is in Olaf Stapledon's Star Maker, written decades before Dyson's paper. Stapledon imagined entire galaxies transformed into cosmic minds, their stars harnessed for computation, a vision eerily close to modern speculations about Dyson bubbles as galactic scale supercomputers. His work didn't just predict the concept, it framed it as a philosophical question, asking whether intelligence at that scale would even resemble humanity's. These portrayals shape how the public perceives Dyson structures not just as engineering projects, but as artifacts of civilizations so advanced they blur the line between nature and artifice. Films like Interstellar and games like Stellaris reinforce this, depicting Dyson swarms as in-game technologies, the pinnacle of a species' ambition. Yet there's a tension in these stories. Sometimes the megastructures are utopian, enabling post-scarcity civilizations. Other times, they're monuments to hubris, their builders vanished or transformed into something unrecognizable. This duality reflects our own anxieties about technology. A Dyson sphere in fiction isn't just a power source, it's a mirror. It shows us dreaming of immortality among the stars, yet fearing what we might become to reach it. The most compelling depictions don't just awe us with scale, they force us to wonder, if a civilization can reshape galaxies, what does it reshape itself into along the way? Sci-fi's greatest contribution might be turning abstract astrophysics into emotional narratives. When we see a Dyson sphere on screen or read about one in a novel, we're not just absorbing a scientific concept, we're feeling its weight, its consequences. That emotional resonance does something equations alone can't. It makes the universe's grandest possibilities feel personal, urgent. And in doing so, it invites us to ask not just could we build such things, but should we, and who we'd be if we did. Not everyone is convinced Dyson bubbles are out there, and some of the loudest skeptics are astrophysicists themselves. One major criticism centers on energy waste. A galaxy-sized megastructure would inevitably radiate heat, and the sheer scale of that thermal signature should theoretically make it easy to spot. Yet when astronomers scan the cosmos, they find no unambiguous evidence of galaxies glowing unnaturally in infrared. Sure, there are anomalies, but skeptics argue these can all be explained by known phenomena, like dust-shrouded starbursts or active galactic nuclei. If Dyson bubbles exist, why aren't they lighting up our telescopes like cosmic neon signs? Another sticking point is material scarcity. The Milky Way contains roughly 200 billion stars, and constructing even a basic Dyson swarm around each would require stripping apart countless planets, asteroids, and moons. Critics point out that there simply might not be enough usable matter in a typical galaxy to pull this off without destabilizing entire star systems. Even with self-replicating machines, the sheer tonnage needed strains plausibility unless civilizations have discovered ways to create matter ex nihilo or harvest resources from other dimensions, which veers into pure speculation. Then there's the timescale problem. Galaxies evolve over billions of years, their stars drifting apart as the universe expands. A civilization attempting to envelop their galaxy would essentially be trying to hit a moving target, constructing megastructures faster than stellar orbits can scatter them. Some mathematicians argue that even with exponential construction rates, the project might take longer than the lifespan of stars themselves, leaving behind half-finished ruins swallowed by cosmic expansion. Communication delays add another layer of impracticality. In a galaxy 100,000 light-years wide, coordinating construction would be like playing chess where each move takes millennia. Without faster-than-light signaling, which physics currently deems impossible, any attempt at centralized control crumbles under the weight of lag. Proponents suggest decentralized AI could solve this, but skeptics counter that no autonomous system could adapt flawlessly across such vast spans without glitches or unintended consequences piling up over eons. Perhaps the most pointed criticism comes from Occam's razor, the principle that the simplest explanation is usually correct. When astronomers see galaxies with unusual infrared emissions, it's far more likely to be dust, gas, or other natural phenomena than alien megastructures. Until we spot something that defies all natural explanations, invoking advanced civilizations feels like science fiction dressed up as hypothesis. As astrophysicist Ethan Siegel puts it, extraordinary claims require extraordinary evidence, and right now we've got dust. But the debate isn't just about evidence, it's about imagination. Critics argue that Dyson bubble theories often reflect human biases, projecting our own industrial ambitions onto the cosmos. Who's to say an advanced civilization would even want to encase their galaxy? They might pursue entirely different paths: digital ascension, black hole computing, or realities beyond space-time. The assumption that intelligence inevitably scales up to galactic engineering could be as short-sighted as medieval scholars assuming aliens would live on planets just like Earth. The skepticism isn't meant to kill the conversation, though. It sharpens it. Every critique forces theorists to refine their models, whether by predicting more precise infrared signatures or exploring alternative megastructure designs that leave subtler footprints. After all, science thrives when ideas are stress-tested, and if we ever do find a galaxy that checks every box on natural dimming, inexplicable heat, gravitational anomalies with no dark matter in sight, the critics will be the first to demand we double-check our instruments. And then, just maybe, rewrite the textbooks. The hunt for galaxy-sized megastructures is about to get a major upgrade, thanks to a new generation of telescopes designed to peer deeper into the cosmos than ever before. At the forefront is the James Webb Space Telescope, already revolutionizing infrared astronomy with its ability to detect heat signatures from the earliest galaxies. While Webb wasn't specifically built to search for Dyson bubbles, its unmatched sensitivity to infrared wavelengths makes it the perfect tool to spot the thermal fingerprints of potential megastructures. Imagine scanning a distant galaxy and finding its visible light dimmed while its infrared glow is oddly intense, like catching the warmth of a hidden engine beneath a cold metal shell. Webb's precision could help distinguish between natural dust clouds and the telltale waste heat of artificial constructs, turning speculative ideas into testable hypotheses. Then there's the Vera Rubin Observatory, set to begin its decade-long legacy survey of space and time in 2025. Unlike Webb, which focuses on detailed observations of specific targets, Rubin will scan the entire visible sky every few nights, creating a cosmic motion picture of unprecedented scale. This relentless surveillance could catch fleeting anomalies, galaxies that flicker unnaturally, stars that vanish without explosive endings, or regions where light seems to be systematically blocked in geometric patterns. Rubin's true power lies in its ability to compare thousands of galaxies over time, pinpointing ones that behave unlike anything in nature. A Dyson bubble under construction might not be a static object. It could grow in phases, its shadow creeping across the galaxy like a slow-motion eclipse. Rubin's watchful eye might catch that progression in action. Meanwhile, the European Space Agency's Euclid mission is mapping the universe in 3 dimensions, tracing the distribution of dark matter with exquisite detail. While its primary goal is cosmology, Euclid's data could reveal gravitational anomalies that don't match dark matter's expected behavior, subtle hints of massive artificial structures warping spacetime in ways that mimic but don't quite align with natural predictions. Similarly, NASA's upcoming Nancy Grace Roman Space Telescope will combine wide-field imaging with high-resolution spectroscopy, allowing astronomers to dissect the light from distant galaxies for chemical signatures that might betray non-natural processes. Could certain elements be unnaturally depleted or concentrated? A side effect of stellar engineering on galactic scales. On the horizon, even more ambitious projects loom. The Square Kilometre Array, a radio telescope network spanning continents, might detect the electromagnetic hum of galactic-scale energy transmission beams or networks pulsing between stars. And future gravitational wave observatories, like the Laser Interferometer Space Antenna, could sense disruptions in spacetime caused not by colliding black holes, but by the deliberate movement of stars themselves. Picture the ripples sent through the cosmos as a civilization rearranges its home galaxy, nudging suns into optimal configurations for their megastructures. The most exciting prospect: these telescopes won't work in isolation. Cross-referencing Webb's infrared data with Rubin's light curves and Euclid's gravitational maps could create a multi-messenger portrait of a galaxy, where inconsistencies across wavelengths hint at something profoundly unnatural. A galaxy that's too dim in visible light, too bright in infrared, and too massive in gravitational lensing without the expected dark matter might not just puzzle astronomers. It could scream intelligence on a scale we're only beginning to imagine. Of course, absence of evidence isn't evidence of absence. If we don't find obvious Dyson bubbles, that doesn't mean they're not out there. Just that advanced civilizations might engineer in ways we haven't thought to look for yet. That's the true promise of these instruments. They'll expand the boundaries of what we consider possible, whether by confirming our wildest theories or forcing us to dream up even wilder ones. The universe's greatest secrets might not hide in the darkness, but in the light we've been misinterpreting all along. Nature has a way of crafting structures so vast and intricate, they blur the line between the organic and the engineered. Take the pillars of creation, those towering columns of gas and dust in the Eagle Nebula cosmic incubators where new stars are born. From a distance, their twisting formations almost resemble the skeletal framework of some unimaginable megastructure, as if the universe itself is experimenting with the same grand designs we attribute to advanced civilizations. These nebulas aren't just beautiful, they're functional, shaping stellar nurseries with gravitational artistry that rivals any theoretical Dyson swarm. Then there are the Fermi Bubble's gigantic gamma-ray emitting structures ballooning from the Milky Way's core. These aren't remnants of alien industry, but the aftermath of our galaxy's supermassive black hole feasting violently millions of years ago. Yet their symmetry and scale are eerily reminiscent of what an expanding Dyson bubble might look like during construction, a reminder that nature can produce geometry as precise as anything dreamed up by intelligence. Even the voids between galaxies, those caverns of near-nothingness spanning millions of light-years, mimic the emptiness we'd expect from a fully enclosed galaxy, its starlight captured, its energy rerouted. Consider, too, the cosmic web, the filamentous scaffolding of dark matter and gas connecting galaxies across the universe. Its branching patterns mirror the decentralized networks a Type 3 civilization might engineer to distribute energy between stars. The difference: one is sculpted by gravity's impersonal hand, the other by conscious design. But the overlap in structure is provocative, hinting that the universe might already hold blueprints for the very megastructures we imagine. Even on smaller scales, nature offers prototypes. Saturn's rings, for instance, are a natural analog to a Dyson swarm, countless particles orbiting in synchronized harmony, each playing a role in a system far greater than its parts. Or take the icy shells encasing distant moons like Europa, which trap oceans of liquid water beneath their surfaces. These aren't artificial enclosures, yet they achieve the same result, harnessing and preserving energy in ways that sustain hidden complexity. The lesson here isn't just about mimicry. It's that the universe operates on principles of enclosure and transformation long before life arises to formalize them. The same forces that birth nebulas and voids could, given enough time and intelligence, be harnessed to sculpt galaxies into something new. When we search for Dyson bubbles, we're not just hunting for alien handiwork, we're asking whether nature's artistry and a civilization's ambition might eventually converge, rewriting the cosmos into forms both ancient and unprecedented. At the heart of every galaxy, lurking like a silent architect, lies a supermassive black hole, a gravitational monster with the power to shape the cosmos around it. If civilizations ever attempt to encase their galaxies in Dyson bubbles, these black holes wouldn't just be bystanders, they'd be central players, either as engines of unimaginable power or as destabilizing threats capable of unraveling the entire megastructure. Consider the energy potential. A supermassive black hole isn't just a void, it's a dynamo. As matter spirals into its event horizon, friction heats it to millions of degrees, creating quasars that outshine entire galaxies. For a civilization building a Dyson bubble, this isn't wasted energy, it's the ultimate power source. Imagine a network of orbital mirrors or energy collectors positioned near the black hole's accretion disk, siphoning off even a fraction of that radiation. The output could dwarf the combined starlight of every other star in the galaxy, providing a backbone for the entire megastructure's energy needs. But black holes are more than just batteries. They could serve as cosmic stabilizers. The chaotic orbits of stars near a galaxy's center might threaten the integrity of a Dyson bubble, but a supermassive black hole's gravity could act as an anchor. Advanced civilizations might use it to park stars in optimal positions, like arranging furniture around a central weight. Some theorists even speculate about artificial accretion disks, structures built to regulate the black hole's feeding, turning a volatile process into a controlled energy tap. Yet the dangers are equally immense. Black holes aren't static. They flare unpredictably, jetting out deadly radiation or swallowing nearby stars whole. A Dyson bubble's delicate infrastructure, spanning light years, could be shredded by a single outburst. Even more alarming, the black hole's gravitational tides might warp spacetime enough to disrupt the orbits of megastructures over time, requiring constant recalibration. A civilization managing this would need technology capable of weathering cosmic hurricanes or perhaps even manipulating the black hole itself, the wildest possibility. Black holes might not just power a Dyson bubble, they could be its architects. Some models suggest that advanced beings could use a black hole's immense gravity to slingshot construction materials across the galaxy at relativistic speeds, or even harness its space-time warping properties to create shortcuts for energy distribution. The event horizon itself might become a computational resource, its quantum properties exploited for calculations impossible in flat space. But here's the haunting twist. If a black hole is active, consuming stars, flaring with X-rays, it could render entire regions of the galaxy uninhabitable, forcing civilizations to build their Dyson bubble in layers, leaving a lethal core untouched. Or perhaps they'd attempt the ultimate engineering feat, quenching the black hole entirely, starving it of matter until it becomes dormant. The very idea stretches credibility, but for a Type 3 civilization, even black holes might be just another problem to solve. In the end, a supermassive black hole isn't just a feature of the galaxy, it's the ultimate test. A Dyson bubble that ignores its power risks catastrophic failure, while one that harnesses it could unlock energies rivaling the Big Bang itself. The difference between chaos and control might come down to who or what holds the reins. Simulating galaxy-scale megastructures isn't just about crunching numbers, it's about bending our perception of what's possible. Picture astrophysicists sitting at supercomputers, inputting variables no civilization has ever attempted. The gravitational dance of billions of stars, the thermodynamics of starlight trapped in matryoshka shells of collectors, the space-time stress of moving entire solar systems into optimal formations. These simulations aren't just thought experiments, they're our only window into understanding how intelligence might reshape reality at scales that dwarf human comprehension. One groundbreaking approach involves N-body simulations, typically used to model star clusters or galaxy mergers, but with a twist. Researchers tweak the parameters to account for artificial structures exerting new forces on stellar orbits. The results are staggering. When even 5% of a galaxy's stars are enclosed in Dyson swarms, their combined mass begins warping the orbits of neighboring systems like invisible hands rearranging cosmic furniture. Over millions of simulated years, strange patterns emerge: stellar streams bending at unnatural angles, clusters migrating toward what would be construction zones, and gravitational microlensing signatures that don't match dark matter predictions. These anomalies could become our cosmic cheat sheet, telling astronomers exactly where to look for real-world evidence. Then there's thermodynamic modeling, which reveals the hidden costs of galactic engineering. Every simulation converges on the same brutal truth: waste heat is unavoidable. A single Dyson sphere might radiate infrared predictably, but scale that up to galaxy level, and the thermal signature becomes chaotic, like a pan of boiling water with endless bubbles erupting in fractal patterns. Some simulations suggest civilizations might combat this by directing excess heat into relativistic jets, firing it out of the galactic plane like a cosmic ventilation system. Others show how they could use black holes as radiators, dumping heat across event horizons where it effectively vanishes from the universe. The most radical models propose quantum energy sinks hypothetical structures that somehow bypass thermodynamics entirely, though no one knows if physics allows such loopholes. Visualization software takes these dry datasets and transforms them into something breathtaking. Run one simulation, and you'll watch a galaxy's spiral arms gradually dim over millennia as megastructures bloom like ink drops in water, first around the brightest stars, then spreading outward in waves. Another simulation might show the galaxy's core transforming into a pulsating network of energy channels, with stars repositioned into geometric lattices that would make Kepler dizzy. These aren't just pretty animations, they're generating testable hypotheses about how partial Dyson bubbles might appear in our telescopes. If a real galaxy shows dimming patterns that match simulation outputs, especially alongside unexplained infrared spikes, we might finally have our smoking gun. The most provocative simulations explore construction methods. One team modeled self-replicating, von Neumann probes building Dyson swarms exponentially, starting with a single seed probe around one star, then fanning out at a fraction of light speed. The results show entire galaxies could be enclosed within 10 million years, a blink in cosmic time. But the simulation also reveals vulnerabilities. A single programming error could trigger a gray goo scenario where replicators strip planets bare without building anything useful. Other models suggest more organic approaches, with genetically engineered biological constructs that grow solar-collecting membranes like cosmic kudzu, adapting to each star's unique conditions. What makes these simulations invaluable isn't just their predictive power, it's how they reveal unintended consequences. Nearly every model shows that stellar engineering triggers chain reactions. Moving stars alters galactic rotation curves in ways that could fling planets into darkness. Blocking starlight halts photosynthesis for any uncontacted civilizations in the galaxy, forcing builders to either relocate them or accept ethical catastrophe. Even seemingly simple acts like mining a gas giant for construction materials can destabilize the orbits of neighboring worlds over millennia. The simulations scream a lesson we're only beginning to grasp. Engineering a galaxy isn't just about power, it's about responsibility on scales we can barely fathom. Perhaps the most haunting simulations are those that fail. Input parameters for a civilization reaching too far, too fast, and watch as their Dyson bubble fractures under gravitational tides or collapses under its own waste heat. These aren't just academic exercises, they're cautionary tales written in math. suggesting that even the most advanced species might face hard limits. The universe doesn't surrender easily to mastery. Every simulation, successful or catastrophic, brings us closer to answering the ultimate question. Are galaxies meant to be lived in, or are we seeing the graveyards of those who tried? The discovery of Dyson bubbles wouldn't just rewrite astrophysics, it would redefine humanity's destiny. If galaxies can be reshaped by intelligence, then the universe isn't a static stage but an open frontier, waiting for civilizations bold enough to claim their place among the stars. For us, still tethered to our pale blue dot, this realization carries both awe and urgency. Are we destined to remain cosmic tenants, or could we one day join the architects? Consider the timeline. Human civilization is barely 10,000 years old, a flicker against the billion-year epochs required for galactic engineering. Yet the mere possibility that such feats exist suggests a roadmap for our own survival. Species that avoid self-destruction might ascend through predictable stages, harnessing planetary resources, then stellar, then galactic. Each leap demands not just technological prowess but cultural resilience, the ability to sustain curiosity and collaboration across generations. The civilizations that built Dyson bubbles likely faced existential crises too, and their survival implies solutions to challenges we've yet to solve: climate collapse, war, resource scarcity. Their existence, if confirmed, would be the ultimate vote of confidence that intelligence can outlast its infancy. But there's a darker edge to this vision. A universe where galaxies are enclosed might already be carved into spheres of influence, with elder civilizations presiding over territories far beyond our reach. Humanity could find itself like settlers arriving on a continent where all the fertile land is claimed. The Milky Way might appear untouched, but what if we're simply in a quiet neighborhood, overlooked until our tech begins to shine too brightly? This isn't just speculation, it's a potential answer to the Fermi Paradox. The Great Silence could mean we're latecomers to a cosmos where the ambitious thrive and the timid remain unseen. Yet even competition carries hope. If other civilizations reached these heights, they did so by overcoming limits we now face. Their blueprints, written in starlight and structure, could guide our own ascent. Imagine decoding the infrared signature of a Dyson bubble and discovering it's not just a power grid but a tutorial broadcasting engineering principles through thermodynamics. Advanced species might leave knowledge embedded in the universe itself, like cosmic breadcrumbs for those clever enough to follow. The philosophical implications run deeper. Encasing a galaxy isn't just about energy, it's about transcending planetary thinking altogether. A civilization that does this likely views stars and planets as raw materials, not sacred objects. For humanity, still emotionally rooted in Earth's biosphere, this shift in perspective would be as jarring as Copernicus proving we're not the center of the universe. It forces us to ask, do we value nature for itself or as a stepping stone to something greater? The answer could determine whether we become gardeners or engineers of the cosmos. And what of our legacy? If Dyson bubbles exist, they endure on timescales that dwarf pyramids and continents. Human achievements today, art, science, even spaceflight, are fleeting by comparison. To matter in such a universe, we'd need to think in million-year increments, planting seeds whose fruits we'll never see. This long-now mindset might be the true marker of a species ready to graduate from local to galactic. The most profound transformation wouldn't be technological but existential. Confirming that galaxies can be engineered would prove intelligence isn't a fluke, it's a force as fundamental as gravity or light. We'd no longer be accidents of evolution, but participants in a grand narrative still being written. The question wouldn't be whether we can build Dyson bubbles, but whether we dare to try, and what kind of civilization we'll become if we do. The Fermi Paradox asks a haunting question: where is everybody? If the universe is so vast with trillions of stars and countless planets, why does it feel so empty? Traditional answers range from the grim civilization's self-destruct to the hopeful they're hiding, but the possibility of Dyson bubbles adds a startling new layer to this mystery. What if we haven't found aliens because we've been searching for the wrong signs? Imagine an ant standing at the base of a skyscraper, scanning the ground for other ants. It wouldn't recognize the towering structure above it as the work of intelligence. Could we be making the same mistake? For decades, SETI has listened for radio signals, the cosmic equivalent of a flashlight in the dark. But a civilization harnessing galaxies wouldn't need flashlights, they'd reshape the night itself. Their signatures wouldn't be brief transmissions, but the slow, stately dimming of entire star systems, the way a forest falls silent when something vast moves through it. The absence of radio chatter might not mean no one's out there. It could mean they've graduated to technologies we can't yet perceive. Then there's the timescale problem. The universe is 13.8 billion years old, plenty of time for civilizations to rise, expand, and vanish before Earth even formed. If a species built Dyson bubbles billions of years ago, they might have transcended them by now, leaving behind relics we mistake for natural phenomena. Their absence could be an illusion of timing, like arriving at a party after all the guests have moved to the after-party. But the darkest interpretation is also the simplest. What if we really are alone? The sheer scale of cosmic silence could mean intelligence like ours is staggeringly rare, or that some universal filter, war, environmental collapse, AI gone rogue, wipes out civilizations before they reach galactic mastery. A universe without Dyson bubbles might be one where intelligence flickers out too soon, leaving galaxies to spin untouched for eternity. Yet there's another possibility, one that's both humbling and exhilarating. Maybe we're not alone, but merely early. The universe is still young, with trillions of years ahead for stars to form and life to emerge. We could be among the first, destined to become the ancient architects future species wonder about. The absence of Dyson bubbles wouldn't be a graveyard marker, but a blank canvas waiting for us to make the first stroke. Ultimately, the silence isn't just a puzzle to solve, it's a mirror. Every hypothesis reflects our hopes and fears back at us. Are we insignificant, overlooked, special? The answer isn't just out there in the stars. It's in what we choose to become as we reach for them. So where does all this leave us? The idea of alien Dyson bubbles, entire galaxies encased in unimaginable megastructures, pushes the boundaries of what we think is possible. We've explored the staggering scale of these theoretical constructs, the physics that might make them viable, and the eerie astronomical anomalies that could be their fingerprints. Yet for all we've theorized, the truth remains just out of reach, hiding in the faint infrared glows and unexplained dark patches of distant galaxies. That's the thrilling paradox of this mystery. The more we learn, the more we realize how much we don't know. Think about what it would mean if we ever found definitive proof. A single confirmed Dyson bubble wouldn't just rewrite astronomy textbooks, it would redefine humanity's place in the cosmos. We'd have irrefutable evidence that intelligence can ascend to godlike levels, that the universe isn't just hospitable to life but malleable to its will. At the same time, the sheer scale of such structures would force us to confront how small we truly are. A civilization capable of engineering galaxies operates on timelines, and with technologies so far beyond us, their motives might be as incomprehensible to us as a skyscraper is to an ant. Yet absence of evidence isn't evidence of absence. The universe is vast beyond comprehension, and our search has barely begun. Every new telescope, every advanced simulation, every fresh perspective brings us closer to answering whether we're alone or surrounded by cosmic architects whose works we're only starting to recognize. That's why this mystery matters. It's not just about finding aliens, it's about expanding our imagination of what intelligence can achieve across deep time. So keep looking up, stay curious. The next great discovery might be hiding in data we've already collected, waiting for someone to see it differently. Or it might require tools we haven't invented yet, ideas we haven't dreamed of. That's the beauty of science. The universe always has another secret ready to astonish us. If this journey through cosmic possibilities sparked your imagination, hit that like button and subscribe for more deep dives into the universe's greatest mysteries. And drop a comment below. Do you think galaxy-sized megastructures are out there? Or is the truth even stranger? The conversation doesn't end here. The cosmos is waiting.